Once we are more expert in navigating through the warm-up and through on the surface of our sample and placing our designs on our desired topographies, we can move towards the CLL panel, so closed loop lithography, where we can manage the TSPL patterning. You can see here the test pattern of the Mona Lisa. In general, from the CLL panel, we can control many parameters that influence our TSPL patterning. You can see here we have temperature parameters, forward height, read height, then patterning parameters, more advanced patterning parameters, feedback parameters, and also saving parameters for our files. In general, these are the most important parameters that we can change while patterning are the following, which were also in the introduction slides of the videos. First one is the temperature, and with temperature we mean the temperature of the resistance of the writer. Second is the force or voltage, is the voltage that we apply between the capacitive platform and the substrate to bend the cantilever. Third, we have the forward height, which is the distance between the tip and the surface of the sample. Then we have the contact time, which from the software can be approximated to the force pulse time, so how long we apply the force pulse for each pixel. And finally, the pixel size or pixel distance, which can be controlled in the geometry. Whenever we import a geometry, we can always change or define a pixel size for our layout. So let's now go back to the NanoFraser software. We will see more in details these parameters and how they affect the patterning, how we can control them to optimize our patterns, so that our patterning skills can also increase. In this video, I wanted to mostly focus on how to quickly pattern effectively with TSPL. In this case, we have an example of a grayscale lithography, the Mona Lisa or Nano Lisa. So let's see. One important thing to keep in mind when dealing with TSPL is that the NanoFraser offers a feedback mode thanks to its closed loop operation. So we can choose a Kalman feedback, a PID feedback, or disable the feedback in case we don't want the feedback. What's important to keep in mind is that once the feedback reaches a convergence state, then we are pretty much happy and the pattern will be in most cases satisfactory. But when it either cannot reach convergence because of saturation of forces or because there is a large overshooting, we may have to adjust some parameters. Another important thing to keep in mind is that when we start patterning the first field with the NanoFraser, the feedback doesn't really know which are good starting parameters for the forces. So this last converged state that is referred to the initial forces that we write for the first line, so this will be the first writing line, will be a guess, and then the feedback will adjust the forces accordingly. So the feedback acts on the forces only, and we will see that when we pattern, all the parameters that we select here are grayed out, so we cannot change them while patterning except the temperature, which can be adjusted. So let's suppose we had to write our first pattern. So it's a test pattern, because the best thing to do, in my opinion, when using the NanoFraser is first doing a nano pattern, which is a test pattern, in this case our Nano Lisa. And then once the feedback reaches convergence, we can pattern on in our desired spots. So let's double check the position of our pattern is not on a pre-existing substrate or pre-existing topography, which we did here, and then go back and we can start our pattern. When we press play, we see that the NanoFraser will perform the IV calibration. So here to check that both resistances of the reader and the writer work fine, and also an approach piezo procedure to find the surface with the highest accuracy, and also it allows us to understand the condition of the tip before we start patterning. Then we also have a trajectory management before we start patterning our design. So we can see here the action of the feedback, because for the first lines that we start pattern, we have a patterning depth which is too, the depth is definitely too deep, so the force is reduced. Probably the forces that we selected here, 3 and 4 volts, are too high, so the force is reduced until we can match the depth, and then after we match the depth, we have the force are still changed because we're dealing with a 3D lithography, but there is no more overshooting in depth in one sense or the other, because the forces, the feedback converged. So now we are already in a good patterning conditions. We see that we pattern with very nice, following very nicely the target depth. So ideally, we can already stop this pattern and then proceed with the official pattern. So this test is already successful because the forces have found a good values. But let's just let it finish, and then we can pattern our, let's say, official pattern. So ideally, in our official pattern, we will not see this initial overshoot of the forces where we're patterning too deep. We will already start patterning at a very good depth, so ideally at exactly at the depth that we need. And in the CLLL tab, we can also have a 3D view of our pattern, so a live view of our 3D topography. So we see our nice Mona Lisa. So the field is almost completed. We see that we also have a bowing correction. In the patterning parameters, we have some corrections, like the fast scan correction, thermal conductance correction, bowing correction. Bowing correction and a fast scan correction are usually not selected or pre-selected when we pattern with the TSPL, because they may also induce, in some cases, some problems. So they are often a solution, but may also cause some problems. So it's also good to know when to apply them, and we will also see this in following videos. So let's move our geometry, and let's try to make the nice Mona Lisa. This is already quite a nice lithography, so it's not going to be much nicer, but we will see how effective it is to use the converged state of the writing forces. So now we move the geometry, we start the pattern again. So we're doing a trajectory management. And now we start patterning. So we see already that the first line is we're not overshooting in depth, we're already patterning quite well. Maybe a little bit too shallow, but it's just one single line, and then immediately we're at good depth. So we don't see that initial region where basically the feedback is changing the force to make the measured depth match with the target depth. Some issues that you may encounter when starting patterning with the NanoFraser is that the feedback can struggle finding a good set of forces. So what you can do is reducing the gain. This is the standard value of the gain, which is 0.8. If the feedback is oscillating too much, you can reduce the gain, or you can also manually change the initial forces to forces that after some tests are more optimal to write. So you can change these initial forces with hopefully a reduced gain of the feedback. You should have better results. Now we see that our Mona Lisa is quite well painted or patterned. It's a good example of grayscale lithography, and in general 2D lithography is even easier to perform once we're not talking about high resolution lithography. But this is a very good example that can be used for understanding how to set up the tool, and also how to properly pattern a field after doing a quick test, adjusting the feedback. And now we have our official pattern, hopefully in our in the location that we want on our sample, and in around 5 minutes, 10 minutes, we should be able to find a good set of writing parameters. So this is pretty much it for the introduction to the TSPL patterning and CLL panel.